Hi guys, welcome to another video. So in today's video, I'll be doing a liquid metal repaste of the Asus Strix 2080 Super. I believe this is a 2080 Super. So this is the Asus Strix model. As you all are aware, Asus Strix models has always been the high-end graphics cards. So this was the highest end for 2080 Supers before we talk about the 2080 Ti, which I've also cleaned and repasted before. So this is how it looks. Doesn't have a lot of RGB, but it's very clean looking, clean black. And before we proceed, I just want to show the temps, like the benchmark temps, before we disassemble the GPU. Okay, so in this case, I was running Heaven benchmark. As you can see, the GeForce 2080 Super ROG Strix Edition. And we can see that it's only 50 seconds into the benchmark, and hotspot temps has already climbed to 104. Okay, if I kind of speed it up, right? If I speed this up to 2x or maybe 3x, yeah, you can see the temps are pretty high. Okay, so here I was trying to show the, I think they show the, let me try and get back that part of the video here. Let me go back to 1x speed. The GPU fan is spinning louder, sometimes due to So the GPU fan is spinning louder, sometimes due to the high hotspot temps. Okay, so in that part of the video, I was trying to showcase the higher fan speed, but I think my phone mic just couldn't pick it up. I was either using my phone mic or my lapel mic, but it just didn't pick it up. So anyway, I'm just gonna skip through this. You can see that high hotspot temps, GPU average temps was about 82, and hotspot here about 105. Also take note of the fan speed. Fan RPM hit as high as 3,491. That's on GPU fan 1. Fan 2 almost hit 3,352. It's pretty high. You can see here, there's the current RPM. It spiked up pretty high as well due to the high hotspot temp. So generally, when it spiked to such a high fan RPM, the fan is a lot noisier. So our goal is to just reduce the temps with a liquid metal repaste. The benchmark is able to complete. We're getting this amount of scores. So in the end, I save this. Okay, so let's proceed with our. Let me open it with VLC because I can speed up with VLC media player. Okay, so this is the disassembly process, and I will probably run this at maybe 3 to 4x speed, and I'll skip through some of it. So first and foremost, I remove the so-called the warranty void when remove the sticker from one of the backplate screws. We do still have this in Singapore, which is really unfortunate, but in my personal experience with one of the Gigabyte GPUs, there is the warranty void when remove sticker, and I did remove it because I did disassemble it for a copper mod, and then after the copper mod, after the copper VRAM mod, the GPU actually died for some particular reason. I'm not too sure whether it died due to my copper mod. So anyway, I replaced it with the stock thermal pads, and I sent it in for RMA, and the Gigabyte distributor actually honored the RMA, and I actually got a new GPU. In that case, the GPU was the Gigabyte 6800. So I don't know whether those stickers do apply, but anyway, here going back to the disassembly, you can see that the paste here is super dried up. So when it's super dried up paste, what I like to do is to use a plastic tool. In this case, this is this is a this kind of a plastic disassembly tool that you use for removing like those game devices or controllers with plastic covers. I use this like a simple soft plastic tool to scratch. You could do it with your fingernails, you could do it with a paper towel, you can do it with anything really. Basically, you just want a soft plastic tool, soft tool. You can do it with wooden chopsticks. You don't want to scratch the metal, but you want to remove the paste, want to loosen it, then I'll brush it off with a simple brush. Right, so that is an easy way to remove hardened thermal paste. You can see me doing the same with the GPU die. So I loosen it because it's hardened and flaky, and then I'll brush it off with a brush it into the dustbin. Then remaining thermal paste, I'll actually clean it off with 99% isopropyl alcohol. Take note to use I've heard from a commenter to use at least like 90 or 95% isopropyl alcohol. To be safe, I just go with 99% isopropyl alcohol. Definitely don't go with the standard 70% isopropyl alcohol that you find in some drugstores or in some antiseptic wound cleaners. Because some of those, if you read the ingredients, it's only at 70% isopropyl alcohol. So those would permanently damage your electronics if you use it to clean them. I personally use 70% isopropyl alcohol, and the results were inconsistent. I was in my early days of electronics cleaning, I was able to successfully clean some of my electronics, but some of the cards died. In particular, I think the 5600 XTs from AMD, and then the 5700 XTs from AMD. I think at least 2 of the cards died, probably due to me using 70% isopropyl alcohol. So far, I've been using 99% isopropyl alcohol, and all my electronics has been safe. Okay, so here I'm just gonna slow it down a bit to probably 2x speed. You can see what I'm using is transparent nail varnish. You can get it very cheaply. It costs about less than $5 from a simple ladies cosmetic store. Personally, I like it to be transparent so that I can see the components underneath. So what I do is this is the GPU die. Surrounding the GPU die, there are like metal bits, and I do not know whether they are SMDs, but if they are SMDs, I want them to be insulated because I don't want any spillage of liquid metal to do any shorting of the sensitive electronics, especially around the GPU core. Actually, even any of the electronics on the PCB, I do not want them to be shorted, because any shorting of electronics might cause permanent damage, and it might kill your GPU. Okay, so I insulate them, and if, like I mentioned in the comments, if any of you are a GPU engineer, if you're an electronics engineer, if you can advise whether are these SMDs surrounding the GPU die, is it necessary to insulate them? Because I've never tried not insulating them. I've always been insulating them so far, and I've ensured that my GPU has always survived the liquid metal repaste. So I've continued to do it because it's a pretty simple step. The nail varnish dries in about 5 minutes to 10 minutes, so very easy to apply as well, as compared to some of the other insulating like gum or gels. So pretty good. I believe Thermal Grizzly by Diabao also has a similar like insulating nail varnish, and they sell it as like a red kind of nail varnish. Yeah, but I think simple nail varnish actually works, and it's a lot cheaper than Thermal Grizzly stuff. Okay, so in this case, I clean off the surface again with 99% isopropyl alcohol, and you can see that stringe that I have is liquid metal. So I apply like really a little bit of a drop. One of the comments said that like a quarter of a drop is not an accurate like measure of how much I should put. But in this case, you can see it's not really like a full droplet, right? It's like maybe half a drop or something like that, half a droplet. The idea is to use as little liquid metal as possible, but to still get an even spread of liquid metal on the surface. So in this case, I think it's a little bit too much, even that half of a drop. So which is why in one of my previous videos, I mentioned to use like as little as a quarter of a drop. Okay. So what you can see me doing is that I'm trying to spread out the liquid metal to be as I'm going to speed it up again, to be as even as possible. So I'm trying to cover like all the exposed surfaces. So spread out the liquid metal, be as thin as possible. So in this case, I realized that I had not enough, so I applied just a tad bit more liquid metal just a bit, just a pinch more. And again, try my best to spread it out. Make sure that all the exposed surfaces on the GPU die and the corresponding cold plate is covered. I wanted to mention that yes, you have to apply liquid metal on both the cold plate and the GPU die, both as evenly as you can, so that when you reassemble the card, the surface tension from both sides with liquid metal meeting up will ensure that the liquid metal doesn't spill out to the side of the components as easily. So I've done this even for like vertically, how should I say, vertically mounted GPUs. That means the GPU where you have the fans facing the side of your tempered glass. So I've done this for one of my water blocked GPUs in my main rig, where it's vertically mounted in the height Y60 case, where you can only vertical mount. So in this case, I've used this method, and the liquid metal has never like leaked or dropped or dipped, right? So the surface tension approach does work, and yeah, just make sure you apply as thinly as possible and as even spread as possible, as even a spread as you can on both the cold plate and GPU die. So just fast forward this a bit. Why you don't want to have any exposed spots on the GPU die is because in my experience, I had actually some instances whereby I was getting like unreasonably high hotspots even after liquid metal. So after disassembling, I noticed that okay, there are just some small surfaces of the GPU die that was not covered, which was why it had this high hotspots. So I just make sure, as you can see, okay, probably here in this, maybe I could get a freeze frame. Let's see if I go back to that. Okay, so freeze frame here. Okay, so in this freeze frame you can see that yes, my liquid metal coverage is a pretty good job, so it's quite even. You can see that there's only some small parts like here, maybe this little parts of the GPU die here is slightly exposed on the edges of the GPU die, which is really minor, so it's really small, but the rest of it is fully covered with liquid metal, as is fully covered, adequately covered, so you don't see any exposed GPU die right through the liquid metal. Some of the liquid metal surfaces here is a little bit lumpy, which means there's a little bit higher concentration of liquid metal. This amount of lumpiness is fine. What you want to avoid is that you don't want to see a big pool of liquid metal. Let's say you have a whole pool, right? It looks like a whole like overflowing drop, or a very even kind of a very liquid kind of pool of liquid metal. Then that is way too much. That amount of liquid metal will spill if you are if you shake your device around. So if you have that much liquid metal, you want to like absorb it. So how you can absorb it or remove it is, first you could actually spray the cotton bud that you're using, because notice I used a cotton bud to spread the liquid metal earlier. You can use a clean cotton bud, dip it or spray it in 99% isopropyl alcohol, and then use that cotton bud to collect and absorb little bits of liquid metal, and then throw it away, or like apply it on like a paper towel and then reabsorb some of the excess liquid metal. The other method is to use your liquid metal syringe that you have your liquid metal with, then aim the tip at that pool of liquid metal, and then you draw the syringe back, like suck up the remaining liquid metal. So that will usually work as well. So if the sucking up method doesn't work, then you use your cotton bud dip with isopropyl alcohol to clean it. Okay, so I think, let me slow down just a little bit. Thing over here, the cold plate. So the cold plate surface is not as important to make sure that you have an even coverage on the cold plate, but I try my best as well. Then you can see that on the cold plate surface I also have an even coverage of liquid metal. Also take note that this cold plate, the 2080 Super Asus Strix edition, is nickel plated. So nickel plated surfaces have no problems using liquid metal. If you have a copper cold plate, there is a commenter in one of my previous videos that said that copper does react with liquid metal. It actually does. So if you do have a copper cold plate, and you spread liquid metal on it, there is a slight chemical reaction. What it does is that it does form a layer of copper oxide, which is like a blackened kind of copper on that surface, and some of the liquid metal on that surface do get absorbed in that chemical reaction process. So in that kind of situation, when you're using a copper cold plate, just apply just a pinch more liquid metal to ensure that even after the chemical reaction occurs and some of the liquid metal is absorbed, you will still have sufficient liquid metal for to conduct thermally. And in situations where if you're using the copper cold plate, very common instances of copper cold plate would be laptop cooling, whereby because laptop cooling is usually using heat pipes, which is copper, and their cold plate is usually made of copper as well. In those kind of situations, it is possible to get your liquid metal absorbed into the tin copper. Then if you see your hotspot start to climb up, maybe after like 3 months to half a year after applying liquid metal, what you need to do is disassemble the whole cooler, and then just reapply just a little bit of liquid metal onto the cold plate or the GPU die again to make sure that it's sufficient for thermal conductivity, and to reassemble it. Then in that after that second application of liquid metal, it should last for, I think, technically forever, because liquid metal technically doesn't dry up. The only situation that it can so-called dry up is that if it gets absorbed into other metals. So if it doesn't get absorbed because the oxide layer is already formed, so it will stay there forever. And does the copper oxide layer affect thermal conductivity? No. So even if you form a copper oxide layer with assuming if this is a copper cold plate, it will still be just as thermally conductive, so it will not affect the performance or the thermal conductivity. Okay, so that's out of the way, and I believe that is all for this disassembly. I think I reassemble the card. Let me see, maybe I speed it up again. Okay, so in this case, I think I reassemble the card. When am I doing it? Okay, so I put it back, make sure that everything sits properly, install the screws. Okay, this is pretty straightforward, right? Install the screws, and I make sure I tighten it in a cross-tighten manner. That means you tighten here, 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 in a diagonal fashion to make sure that you get even pressure on the GPU die. Okay, then I insert the rest of the screws. Wait, where was it? The rest of screws. Yep, so all the screws are in, and then let's go and test it. That is after repaste, right? So the 2080 Super Strix version is in my test bench. It boots up, and we run the benchmark. So Heaven benchmark ran. Okay, and we start up the. Okay, so HW info is already started up. So let's just fast forward a little bit and speed up the benchmark. So you can see that even 1 minute after the benchmark, right, hotspot is only at 60. Average GPU temps is 49. So if I were to take a look at the previous video before repaste, we can compare the temps. Okay, so this was the previous temps. Let me maybe make a side by side. Alright, so this is after repaste, this is before repaste. Okay, so before repaste, about 3 minutes into the benchmark, the hotspot was at 105, right? Highest at 105. So in this case, maybe let us go to 3 minutes as well into the benchmark. Highest hotspot, GPU hotspot, was only at 71, right? So this is more than this is a reduction of about 34 degrees Celsius, which is a big reduction in the GPU hotspot. And average GPU temps max out at 61 after repaste. Before repaste, it was at 82. So this is a reduction of 21 degrees Celsius, which is also another big reduction. The fan speed also has significant reductions as well. So before repaste, the fan speed hit a max of 3000, almost 3500 RPM. Let's round it down to 3400 RPM. After repaste, the max fan speed is maxing out as 1007. So it's a lot quieter. So the fans spin up less, it's not as noisy. And if I forward us through the benchmark, you can see that we complete the benchmark. And this is about how many minutes in? I think my phone went off. Okay, and you can see that in this case, okay, so this is after liquid metal repaste, right? So HWD info has been running for 14 minutes. At 14 minutes of Heaven benchmark running, the maximum GPU hotspot has not exceeded 75 degrees. It hit 74.5, currently at 73, and then the average GPU temps just maxed out below 65, so it's at 64.2. The good thing about the fan RPM as well is really quiet, so it's only averaging at 1800 RPM, which is a lot. It's like almost half the RPM as compared to before, which was it hits about almost like 3005. So at half the fan speed, with about 20 to 30 degrees reduction across the board. But of course, you wouldn't get such a drastic improvement if the paste on your GPU has not dried up yet. So in this example, liquid metal is really extreme because the paste on the customer's GPU has already dried up. It's already dried and flaky, which is why it is overheating. But if you have a perfectly working paste, you won't see as high of a temperature improvement. But if you have paste that's dried up and you're using liquid metal, you can see significant improvements in it. Alright, so that's it for this video. So if you have any questions about liquid metal, cooling for your GPU or your CPU, please post in the comments and ask away. If you find this content useful, maybe give the channel a subscribe, as I'll be doing more and more of this content. Okay, we'll see you guys in the next video.